So let's get into specific heat and heat processes that involve a change in temperature. We'll have a lot of these problems in chemistry. Sometimes this is as a result of a chemical system releasing heat into like the water or the container, or sometimes this is due to adding a hot object to a cold object. But once I have the condition for temperature change, I can make problems revolving around the specific heat. So the specific heat is simply a constant that is defined as the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degrees. And this is just changing the temperature, no state changes are involved. I could actually have a molar specific heat, and the only difference is it's per mole of substance rather than per gram of substance. So we see that we use the variable CP, and by the way, every single physics and chemistry textbook seems to have a difference. Some of them call them CP, some of them just call it capital C, sometimes it's an S for specific heat, so it can vary, but if you look at the units will always be consistent. So we're going to use the variable C with a little subscript of P, and that really implies that this is happening at a constant pressure. That the heat absorbed per mass per degree Celsius rise. And so we use Q to represent heat. That's the heat absorbed by a sample. And again, it's defined as absorbed, so that if heat is released by the system, it would be a negative value. And we have M. M is referring to mass. And we have delta T. And delta T is defined as a rise in temperature. So sign again matters. If the temperature is dropping, it's negative. The best way to calculate delta T is to always say the final temperature minus the initial temperature, and then the sign will be revealed in the what it happens to work out. And so you don't have to be as worried about, did I get the sign right? If you always do this final temperature minus the initial temperature to calculate delta T, you'll be fine. Anytime you see the symbol delta in chemistry, we're talking about a change between the final and the initial. So we'll see delta H, we'll see delta T, we'll see delta E. So that's a general statement that that word delta is always a cue to have the final variable minus the initial variable, whatever property we're discussing. So the way we will typically use this is going to be this second formula. The Q is equal to MC delta T. These specific heats will vary for different substances, and I can go look them up in some reference table. You do want to watch out. We will have to look them up, and when you look them up, you're going to have to watch out for units, because they can vary. I could have either joules or calories or kilojoules or kilocalories per some unit of mass, usually grams, but sometimes per kilogram, and sometimes in large systems, they sometimes even have it per pound, and then per some kind of degree, some temperature in degree, so usually degrees Celsius, occasionally Kelvin. And I have different substances and different values, so I can go look these up if I need them. This is what a specific heat problem would look like. How much heat is absorbed when 13 grams of water goes from 23 degrees Celsius to 30 degrees Celsius? So I notice that there's a change in temperature, and they're not talking about any chemical reactions involved. So I'm thinking, okay, this is a straight up specific heat problem. It also lists, although I forgot to change the S to CP. So some variables use S, and I was converting over from the last book and I forgot, I missed this one. So the specific heat that should be CP of water in its liquid state is 4.184 joules per gram degree Celsius. Not only does the specific heat change per substance, it's also different for different states of that substance. And we'll generally be dealing with liquids in our problems, but it doesn't have to be. So heat is equal to the mass times the specific heat times the change in temperature. 13 grams is the mass. They've given me the specific heat as 4.184 joules per gram degree Celsius, and I'm going to use my final temperature, which is 30, minus my initial temperature, which is 23, to calculate the delta T. Here I've calculated delta T. It's a positive value in this case because it's increasing in temperature, and I get a calculation of 380 joules. Here's a different version. How much heat is absorbed when 9.6 grams of water goes from 85 degrees Celsius to 30 degrees? Note that I'm actually decreasing in temperature, so the difference is when I use my final temperature of 30, but my initial temperature is 85, I'm going to get a negative delta T, which results in a negative answer. So since this was written as how much heat is absorbed, this is talking about the definition of Q, I would enter negative 2200 joules. But if it had said how much heat is released, since Q is defined as an absorbing of heat, if it's released, I would need the negative of negative 2200, which would be entering a positive value. Some hints about specific heat problems. One is that it's only applied to processes where the temperature is changing. That's what this is referring to. Specific heat is about temperature changes of one substance without a chemical change involved, without a state change involved. If I have a state change or a chemical change, I need a different equation. The equation is mass. Heat is equal to mass times specific heat times the temperature change, and the temperature change is always defined as T final minus T initial. I will often have to look up specific heat values if they're not given straight in the problem, and sometimes they're in joules per grams degree Celsius, and sometimes they're in calories per grams degree Celsius. They could also be per mole instead of per gram. Pay attention to the units because I may need to do some conversions if they don't cancel out. Remember that cooling will be a negative process, so that I have a, because when the system is cooling, it's releasing energy to the surroundings, and so it should have a negative delta temperature and it should have a negative heat. And also be careful that we're only involving temperature change, no state changes. It can't cross over the boiling or the melting point, and it can't involve any chemical reactions. Here are two sample problems that we will work in our class.